Hi, everybody. Happy Monday. I know it's not Monday when you're watching this, but it's Monday when I'm recording it, and I don't get to say happy Monday anymore to anybody because I don't teach any classes on Monday. It's very awful. So I'm just going to tell you happy Monday because it's Monday for me right now. All right. So we are starting the next section, which is polygons. Okay. And we're just going to start by going through some definitions here. So a polygon, first of all, is a closed figure, okay, whose sides are segments that intersect at their endpoints. Okay, so if you look at that definition, there's really three things here that you need to be a polygon. Okay, so the first thing would be it has to be a closed figure. Okay, the second thing would be that the sides are segments. And then the third thing is that the sides intersect only at the endpoints. Okay, so they intersect at the endpoints. So you really need those three things to be a polygon. A regular polygon just means that all the sides are the same length and all the angles are congruent. Okay, so regular polygon, all sides are same length and all angles are congruent, which just means equal. Okay, so if we look at some examples here, if you look at the first three shapes here in this box, these would be polygons. Okay, so they're all closed figures, they all have sides or segments, and they all intersect at their endpoints. So these are all polygons. Okay, in the next box here, if you look at these, they have the tick marks on the sides and the markings on the angles. So all these sides and angles are congruent. So these would actually be regular polygons. Okay, and this last one, if you look, there's curved sides. This first example, the segments aren't intersecting at the endpoints, and here they're going through, they're intersecting, but not just at endpoints. So these are all not polygons. Okay. So when we have polygons, we also have different types of polygons. So we have convex and concave polygons. So a polygon is going to be convex if a segment joining any two interior points lies completely within the polygon. So what that means, like if you look at this first shape here, if I draw a segment anywhere inside the shape, it's always going to stay inside the shape. Okay, so if I draw a segment joining any two interior points, it's going to be completely inside the polygon. Okay, whereas a convex polygon is a polygon where it's basically the opposite. So like if I draw a point here and a point here and I connect these 2 points, you see how this is outside of my figure? That makes it concave. Okay, so concave, it's kind of what it sounds like. It caves in or there's a dent in it. But really it means like you could draw 2 points anywhere within the figure and, at some point here, it's outside of the figure. So that's concave. Convex is if you draw points anywhere and they're always inside the figure. Okay, concave, cave in. All right, so then we also know the different names for different types of polygons here. Okay, so hopefully we all know that if it has 3 sides, it's a triangle. 4 sides, make sure you say a quadrilateral. So some people, will say a square or a rectangle. That's a specific type of quadrilateral, but in general, quadrilateral is 4-sided. Okay, 5-sided is a pentagon. 6-sided is a hexagon. 7-sided is a heptagon. 8 is an octagon. 9 is a nonagon. And 10 is a decagon. Okay, for right now, there are specific names for figures that have more than 10 sides, but what we're gonna say, I'm not gonna make you know them. So like, if it's 12-sided, you would say a 12gon. If it's 30-sided, you would say a 30gon. Okay, so basically an n-gon, and n just represents the number of sides. Okay? So now we're going to look at classifying these types of polygons, if they're a polygon or not. So this first one is going to be easy because it's not a polygon. So we don't actually have to do the name. It's not regular or convex or concave. So the only other thing we have to answer is if it's not a polygon, why not? So this is not a polygon because it has the curved sides. Okay. Number 2, it is a polygon. Named by the number of sides, so it has 1, 2, 3, 4, 5 sides, which would make it a pentagon. Okay, regular, it would not be regular, right? So the sides and angles are not the same, so it's not regular. And this one would be concave, right? So see how it caves in here? And again, if I were to draw a segment connecting 2 points, here it's outside of the polygon, so this is concave because it's caving in. Okay, number 3, that is also a polygon. And the number of sides here, so 1, 2, 3, 4, 5, 6. Okay, so a 6-sided figure would be a hexagon. Okay, this would be regular because it has all the markings besides the ones that I drew here, but it has the tick marks and it has the angle measures. Okay, and then this one would be convex because it doesn't cave in anywhere. So anywhere I draw 2 points here and connect a line segment, it's always going to be inside my polygon. All right. And number 4, this would not be a polygon, right? Because it's not a closed figure. Okay. So those are just some examples that you can kind of use to figure out if it's a polygon or not. All right, so now we're going to move on here. Oopsie, these are already filled in. To angles inside of a polygon. Okay, so interior angle is just an angle that's inside of a polygon. Okay, and we also know the sum of the interior angles is just the sum of all the angles inside of the polygon. Okay, so this is how to find the sum of an interior angle of a convex polygon. So where n is the number of sides that it has. So for example, there is a formula that we're going to kind of use here. And if we look at this triangle up top, we know that the sum of a triangle, all the angles inside of a triangle, should sum to 180 degrees, okay, because we just know that. But if we get to something, like an octagon or a nonagon, we don't necessarily just know the sum. So there's a formula that you can use, which is the number of sides minus 2 times 180 degrees. So for example, with the triangle, if we didn't know it summed to 180 degrees, we would have done 3 sides minus 2 times 180 to get the 1 times 180, which gives us 180 degrees. Okay, so for like a quadrilateral, this is a 4-sided figure, right? So we would do the formula here, and we would plug in the number of sides, 4 minus 2, times 180 to give us 2 times 180, which is 360 degrees. Okay, so we know the sum of the interior angles in a quadrilateral is 360 degrees. So for number 2 here, we're going to count the sides. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we know it's an octagon. All right, so to find the sum of all the interior angles, we're going to say the number of sides minus 2 times 180. Okay, so then I would be doing 6 times 180, which would give me 1,080 degrees. Okay, so the sum of all of the interior angles would be 1,080 degrees. Okay, so we're going to move on then to just finding the measure of one interior angle, and this can only be for a regular polygon. So remember, regular means that all the sides are equal, all the angles are the same. Okay, so that's why we can only do this for a regular polygon. So the formula is still n minus 2 times 180, okay, because this gives us the sum, but now we're going to divide it by the number of sides. Okay, because if we divide the sum by the number of sides, it's going to give us that one interior angle. And we can only do this because we know that they all are equal. So here, so I have a 1, 2, 3, 4, 5, 6, right? So I have a hexagon. So I know it's 6-sided. So I'm going to do 6 minus 2 times 180. And I get 4 times 180, which is 720. And that's the total, that's the sum. Okay, but I want one interior angle. So because I know these are all the same, because it's regular, I'm going to be able to divide this by the number of sides. So the number of sides is 6. So if I divide this by 6, I know that each angle is 120 degrees. Okay, so this is each angle. All right, so the sum, we still do n minus 2 times 180, but now if we want to find one interior angle, we divide it by the number of sides and get 120 degrees. Okay, so same thing for number 2, it's a regular nonagon, so I'm still going to find the sum. So nonagon is 9 sides, so 9 minus 2 times 180. Okay, so I'm going to do 180 times 7 to get 1,260, and this is the sum. I want to find one angle, so I'm going to divide it by the number of sides. So I'm dividing it by 9, and that's going to give me 140 degrees. And again, this is each individual angle. Okay? All right, so that's for interior angles. For exterior angles, okay, an angle that's outside the polygon when you extend the side length. So all these numbered angles here would be exterior angles, okay? So for any and all polygons, the sum of all exterior angles is always 360 degrees, okay? So no matter what type of polygon it is, it's always going to sum to 360 degrees. So this says how to find the measure of one exterior angle, and again, it has to be a regular polygon. Okay, so to do that, if it's regular, they all have to be the same. So we're just going to do 360 degrees divided by the number of sides. Okay, so it always has to sum to 360. So find one exterior angle of the following. So a square, again, I know the sum is 360 because it's always going to be 360. I'm going to divide it by the number of sides to get 90 degrees for each exterior angle. Same thing here with a regular hexagon. I know it has 6 sides, so the sum is still always 360. I'm going to divide it by the 6 sides to get each exterior angle of 60 degrees.